Well, the context of the work is the explanation of Bayesian networks, and basically we can distinguish three types of explanation. One is the explanation of the model itself, for example, the graph, the way it looks. Then we have explanation of evidence, such as MAP and MPE explanations, and I'm sure Johan will talk about that next. And the third is explanation of reasoning, which is basically meant to justify the outcomes you obtain while reasoning with the network. So we assume we have entered some evidence into the network, and the example network that is shown here is the child network, which models the diagnosis of congenital heart disease in babies and small children. And here we see an example where evidence is entered for 4 of the variables. These are indicated by the red bars in the histograms. And the network predicts, in this case, a distribution over the outcome of interest, the disease variable, where in this case, one of the outcomes is clearly the most likely one. So I talked about this in my course on Bayesian networks, my master's course, and then one of the students came up to me and said, okay, I like this topic. Can I do something about explanation in Bayesian networks? And I said, well, sure. Go ahead, have a look at what has been done, and also at have a look at Explainable AI and what they're doing in machine learning. Because in machine learning, often explanation is about contrastive questions that ask about outcomes that are not obtained. So why do I get outcome T instead of some other outcome T prime? And they use what they call counterfactuals. Now, this is a term that is used in many different ways, but they are typically defined as the change in input that is required to change some outcome from T to T prime. And note that in this case, we're really looking at a targeted explanation. So we're looking at why don't I get some expected outcome T prime and not just any other outcome than T. So somewhere around December 2019, Tara came to me and she said, okay, let's use counterfactuals to explain Bayesian networks because these have not been used in this context before. And then the outcome of the network in our case would be the most likely one. Note that since then, a lot of research has been done into introducing counterfactuals also into explanation of Bayesian network classifiers specifically. So, and even while this paper was under review, more papers very similar were published. So it was apparently a very timely topic to discuss. So what we propose is that the combination of the more traditional justification of the outcome we do obtain with an answer to the contrastive explanation. Okay, why didn't I get this expected outcome T prime? And the first is supposed to persuade the user that indeed the outcome the network is giving is the outcome it should give. And we call this a sufficient explanation. And this term is also known under a lot of other terms, such as prime implicant explanation or sufficient reasoning, and also the abductive explanations are very similar to this. And a sufficient explanation in our case is a minimal subconfiguration of the evidence we did obtain that already suffices to conclude the outcome, a most likely outcome we find, regardless of what you would get for the other variables you observed. The counterfactual explanation is a minimal subconfiguration also of values of the observed variables, but now the values that are not observed. So it's a change in values for some of the observed variables that, in combination with the remaining evidence, would suffice to conclude the expected outcome T prime. So if we think about, well, we've got these nice definitions, but if we think about how to establish these explanations, then, well, the number of potential sufficient explanations is exponential in the size of our set of observations, because we have to consider all possible subsets. The number of potential counterfactual explanations can even be somewhat larger because we have to take into account all possible other values of the variables that are observed. And to determine whether they result in an outcome T or an outcome T prime, we need to do probabilistic inference to determine what their outcome is, and probabilistic inference is empty hard. So we need to find a way to cope with that. And fortunately, there are various properties of the explanations we defined, which are listed in the paper. And I'm not going to discuss them here, but they do allow us to do a breadth-first search, which we will now call the BFS SFX for sufficient explanation and CFX for counterfactual explanation on a subset lattice, which we annotate dynamically so as to limit the number of computations we actually need to do. So this dynamically annotated subset lattice is what we call the explanation lattice. And I've given a small example right here where the set of observed variables is x, y, z. So you see all possible subsets of those variables in the lattice here in the image. And each subset, so each lattice element will be annotated with three things. The first is the subset of the configuration or the subconfiguration of the evidence that corresponds to the variables in that element. So for the top one, where we have all three variables, for example, we have the actually observed evidence x1, y1, z1. And if you would go to xy, then you would only find xy, y1, etc. And these are all explanations that are potentially sufficient. And because we want to find the smallest ones, we would basically have to go further down into the lattice to try to find them. Then another thing we annotate every lattice element with is all pairs of potentially counterfactual explanations. So these are subconfigurations of other values of the variables involved. So for example, if we look at variable z, we've observed value z1, and suppose it has three different values, so we also have z2 and z3. Then in lattice element xy, the z is missing. So for the non-observed values of z, c2 and c3, we have labeled those pairs, listed those pairs, and they all have a label. And the label is the outcome of the model if we use that combination of values for z in combination with the actually observed values for x and y. And well, suppose that here for z2, I've computed the outcome of x1, y1, z2, and I've got actually the expected outcome. So this is a counterfactual. And for C3, it's still unknown because I haven't done the computations yet. So initially, these are all unknown, and we don't do the computations until we actually need them. The third thing that every lattice element is annotated with is a label which is either true, exp, or other, and initially, again, empty, because we first have to do the computations of all the pairs that are associated with a lattice element to know what this label is. True means all the computed outcomes of all those potentially counterfactual explanations are true. So these are not counterfactuals, but actually indicate that there may be sufficient explanations, either these or further down in the lattice. So it's basically a cue for continuing the search for sufficient explanations. X means that all the outcomes associated with the pairs are the expected outcome T prime. So that means I found counterfactuals, and in fact, I cannot find any smaller ones. This is the smallest I have, so I don't have to continue further down the lattice, because continuing further down the lattice means that the counterfactuals would become larger. So I can stop the search for counterfactuals there. And in all other cases, so a mixture, but it could also be a third value because I'm not limiting my output to two values. That means there can no longer be smaller sufficient sets, so I can stop the search there, but there could still be counterfactual sets, explanations that I need to explore. So this roughly gives you an idea of the search structure on which we're doing the search. And we see the labels that are basically indicating whether we should continue the search or not and search for either sufficient or counterfactuals. So I would just like to give you an idea of how this works with an example. So again, this child network with the same observations we saw before, and the outcome that is most likely is RT. And there's another, in this case, very unlikely one, which is RT prime, the expected outcome. So these 4 observed variables, I've given them labels in short, HOCX, from left to right as in the image. And so this is the subset lattice we get for these observations. And we now start the search at the top, first searching for sufficient explanations. Here between brackets, you see the number of configurations for which I have to do a computation and the number of, or the number of configurations that are in the subset element, and the number for which I actually do the computations. As long as I'm looking for sufficient explanations, these numbers will be the same. And in the root, there's only the combination of actually observed evidence. And then I can continue the search there. And here we see that we've processed all the children, and that means I've actually computed the outcomes of all the pairs associated with those elements. And 2 of them are true, which means I can still have sufficient sets in their children. So I continue the search for sufficient explanations there. The others are labeled other. And for the left one, the HOC, that actually means that there is a value of X that is a counterfactual. So here we use a different queue for our breadth first search that is already initiated to do the search for counterfactuals later on. And also the other one, there is no counterfactual associated with this one. There's no value of H that would give us a counterfactual explanation, but there may possibly be others. So we enqueue those in the queue for counterfactual explanations as well. So we continue, and in fact, we find the only sufficient explanation that we have in this case right here. So we see that all ancestors in the lattice have labeled true, and that's the condition we need. And we find an explanation with values of H is yes and X is some other value. So now we can stop because we know that all the other ones that were enqueued in the queue for sufficient explanations don't have those true labels for all their ancestors. So we're done here, but we were still looking for counterfactual explanations, and we had initialized that queue before, so we can continue there. And what you see now is that the numbers here, the number of pairs for which we actually compute an outcome compared to the total number of pairs that are listed there is decreasing, because if we have a counterfactual explanation for some value of X right here, we don't have to try that combination with that value of X anymore, because it's already the smallest one we find. So we remove pairs from all those descendants. Here we find another counterfactual explanation, and we continue the search. And in this case, we have to go all the way down to the bottom element, but you see that the number of computations we have to do compared to the worst case is reduced. And we find for these 3 lattice elements, we find actually 4 different counterfactual explanations. So that was just to give you an idea of how the algorithm works. Breadth first search with 2 different search queues on a dynamically annotated lattice element to compute a combination of sufficient and counterfactual explanations, which we call persuasive counterfactual explanations. And well, a number of optimizations are possible. First, to speed up the inference of the probabilistic inference itself when we do computations in the Bayesian network. And another one is to further prune the number of combinations we have to compute probabilities for in the lattice And that is by exploiting monotonicity properties. So we know, for example, that a higher value of an evidence variable can only decrease the probability of a higher output, whereas we're expecting a higher ordered output. So in future, we would like to see if we can make more use of the Bayesian network we're using, other than just input-output combinations that we're doing now, by also including intermediate variables in the explanation. And perhaps also use the probability distribution if we have to select from many explanations to return to the user. Okay, hopefully I've persuaded you into thinking that this is a very nice research, and I'll take any questions.
Thank you, Celia, very much for an interesting talk. Thank you for such a demonstrative example. And first, I would like to ask whether there is a question in the audience. So please.
Yes, how would you select the T prime, the expected value in practice? Because there's so many values to choose from.
Okay, so Celia, in case you didn't hear, the question is, how do you select T prime? Because there is a lot of options.
We're assuming here that that is input by the user. So we're trying to explain this output to the user, and then the user says, okay, I see that you're returning T, but I had expected T prime.
Yeah, well, this question would need better elaboration in the break.
Next week.
Milan, do you have one?
Yes, I have one later question. So, is it computationally demanding to compute this counterfactual? So, or how big lattice it's still manageable by your approach?
Well, this will be determined by the number of observed variables. And then the number of computations we have to do is also determined not only by the size of the lattice, but also by the number of basically configurations that you have for those variables. Because for the counterfactuals, you also have to consider the non-observed values. So it's, I would say, highly demanding, and therefore, well, as the slide says, the breadth first search on the lattice is actually model agnostic, because we're not really using any properties of the Bayesian network apart from computing probabilities from them. But it is a technique that is only suitable for situations where you have only a limited number of features. So for any deep learning neural network approaches, this would not be a suitable approach.
Thanks.
Thank you. And I saw, if I saw correctly, one question from Nico. Is that right?
Oh, thank you. The question has actually been answered. So
It has been answered. Okay, perfect. So as we are out of time, so I will ask one final question. And the question is, Celia, whether you think this research will help in the fight between Bayesian networks and neural networks. It's a little softer.
Well, we often say that Bayesian networks are preferable to neural networks because they are interpretable by themselves. I'm not sure I necessarily agree with that, but I think that with the Bayesian networks, we can more or less live with the popularity of explainable AI and make some progress here as well.
Okay, so that was basically yes, right? Perfect. Thank you very much again. And as our second speaker for the last session, I would like to invite Johan. Well, I'm very uncomfortable with Netherlands surnames. Quist-Hout, was that at least a bit correct? From AI and artificial intelligence in Radboud University, and the talk will be about explainable AI using map independence. So, Johan, the screen is yours.
Yeah, thank you, Martin. It's Johan Christout indeed, and Dutch names are indeed very notoriously difficult to pronounce, so I'm able to help you here. He's from Lattice University, calling you from the Netherlands, and in the Foundations of Natural Stochastic Computing group, we have different research lines, including some investigating particularly spiky neural networks, but the one that is maybe closer to my heart is the one where we study properties of Bayesian networks, in particular explanations in Bayesian networks, and this talk is about explainable AI in terms of explanations in using the so-called term map independence. So this is what we'll cover today. So we'll look into some introduction, and we'll spend quite some time to give a more intuitive introduction to the problem, look into a running example, we'll give a formal definition of the problem. Yeah, if you know me, there must be some complexity proof in any talk I give, so there will be some combination considerations. And we'll look also in the conclusion and future work. Oh, yes. And I have to say that some of the future work is already to some extent taken care of by the previous work by Celia and her students. So I think these are very topical research talks with respect to that.
Yeah, Johan, I was waiting for the break. You're not sharing screen so far.
So you don't see my overview slide?
No.
Okay, and let me maybe try to just stop sharing and share again. Do you see it now?
Yes, we do.
That's better? Okay.
Thank you.
So this was basically the overview slide that gives you the overview of the talk here. Now I need to think about how to, yeah. Okay, so the topic here is explainable AI, and as Cecilia already indicated, it's a hot topic in artificial intelligence. It's becoming more and more relevant. Now AI models are, to some extent, in some areas, surpassing human capacity. So think about, for example, a game of Go, where AlphaGo Zero basically outperforms the world champion, but cannot explain to the audience why it made a particular move that sort of baffled the audience that didn't expect a particular move. So and that is interesting from a game perspective. I think it's more relevant even from the clinical context, where you could have, for example, a deep neural network that could classify a CT scan way better than a human expert could. But if the AI then would say, well, you should operate here in this tissue, but I cannot explain you why, then no surgeon would take that for granted and take the responsibility of operating a patient if there is no clear indication why the AI system came to a particular decision. So explainable AI, opening up these black boxes is very topical and very important. The context of this course is indeed in decision support systems, clinical systems in principle. And we make the assumption that under the hood of this decision support system, there is a Bayesian network that describes the relations between the findings, the test results, the observations, the patient report, and the diagnosis, the hypothesis. And the goal here is to find the best explanation, the diagnosis that is most probable given the evidence. So given this explanation, and indeed, as suggested, Bayesian networks are not so much black boxes as deep neural nets, in the sense there is semantics associated with the variables. But still, we think that even if this decision support system could give this particular explanation, so that joint value assignment lowercase h, which has the maximum posterior probability given the evidence, it still is a bit of a black box, because there is no reasoning behind that justifies why h and not some h prime would be the best explanation. It does not give insight to the human user whether the decision support system is good at its job, knows what it's talking about, and what the reasons were for seeing this as the best explanation. So the question is, does this actually explain anything? It's a sort of a circular argument. If you say that A star is the best explanation for some piece of evidence E, because it comes out of the equation as being the best explanation. And this is particularly relevant because if you are solving the map problem, maximum a posterior probability problem, you are marginalizing out intermediate variables that are neither part of the explanation set nor part of the evidence. So we want to, in this paper, introduce a notion of justification, of these map explanations. So the goal is somewhat similar to Celia's goal. We approach it from a different angle, and we want to explain and justify a particular explanation in terms of the variables, the intermediate variables, that were relevant towards ending up in that particular explanation. So that's the purpose of this paper. So we built to some extent on early work by Judea Pearl, and this is an example from a 1987 paper. Pearl advocated the view in this paper that human reasoning is largely built up upon the notion of conditional dependence and independence in knowledge structures. So the idea and the example he gave here is that my neighbor's car and my friend's car are independent. So for example, properties of the car, the color, are independent, but they may become dependent and the relation may become relevant upon discovery of some observation. So let's say that my friend comes over for dinner, and when she leaves, she tries to open up my neighbor's car and then realizes that it's the wrong car. She mistook his car for her own. And then upon observing that particular fact, we could say that the color of my neighbor's car and her car becomes dependent on each other. It's likely to be the same color in addition to other properties of the car, rather than her car being red and my neighbor's being gray, for example. And so upon observation of this fact, these two variables become conditionally dependent, and Pearl used that as an example to say that upon deciding what is relevant in a particular context, we should look at conditional dependence and independence to see which variables are relevant, those that are conditionally dependent, given evidence, and those are irrelevant. So to flesh it out a bit more in an abstract example here, let's say we have this particular small Bayesian network, and I omitted the probability tables here, just focusing on the graphical structure. Let's say that we were interested in deciding upon the best explanation of evidence C, and we're interested in the explanation for variable A. In order to compute that, we need to marginalize out the intermediate variables, and that is D and B in this case. And note that if you look at Pearl's definition of which of these variables would be relevant, then D would be irrelevant because D is conditionally independent given observation for C. D is deseparated from A, and B would be relevant because B is obviously not deseparated from A. And while we think this is a good start in Pearl's work, we would like to take it a bit further and zoom into the contribution of variable B to the explanation of A given C. And the reason why we want to do so is that by marginalizing out variable B in the determination of the best explanation, we sort of lose information about variable B and the contribution of variable B towards explaining A. That may become interesting to see whether that contribution is big or small in order to determine whether that information is relevant in justifying why A is the best explanation of C. So taking this network structure as an example, I wanted to interpret that in a sort of a topical example here. And the question would be here, the same structure, A would now have the meaning, can I attend a festival? C is a question, did I buy a ticket? D would be, do I have money for a ticket? And of course, if I know that I already bought the ticket, then the question whether I actually had the money to spare becomes irrelevant because it's deseparated. And in this example, B would be the question, do I have a valid COVID-19 QR code? Now, under the assumption that there is a high vaccination rate and a low incident rate, then the prior probability of B being true would be large. And given the natural conditional probability distribution, you would assume that when marginalizing out B, the best explanation for the variable A, can I attend a festival, given that I bought a ticket, would be yes, you can attend, marginalizing out this variable B. Now, in the case that B would have been observed to F, to false, then the situation would be different. So here, the fact that B is not observed to a particular value actually makes a difference. It had B been observed, and would it be false, then the explanation would be different than in case B would be observed to be true. And in this case, B is not observed at all. And in this case, you could argue that B is relevant in explaining why I can attend the festival, given that I have the money. Given that I bought the ticket. So B plays an explanatory role, and you could justify the decision by elaborating on the fact that I did not find any positive test result, for example, in the variable P. Now, if you take another example and have a different interpretation for B, for example, do I wear glasses? And sorry for the typo here. Assuming that this doesn't depend, the fact that I can attend the festival does not depend on whether I wear glasses or not, might assume that this does not influence the inference of A, and the best explanation of the evidence would still be the same, independent of whether I would observe this to be true, to be false, or to keep it unobserved. And so the observation of B would not change the interpretation of the best explanation. So here you could argue, zooming into the contribution of B to the best explanation, that B is irrelevant in determining this explanation. So this is an example that motivates why you would want to look into these intermediate variables that you marginalize out to see whether they have a contribution to the explanation or not. So we formalize this problem as follows. We call it map independence. We have as an instance a Bayesian network and a forpartition of the variables into evidence nodes, which could be empty, an explanation set that has a particular joint value assignment, a non-empty set of nodes R, for which we want to decide whether they are or are not independent relative to the explanation, and a set of intermediate variables. And then the question is it the case that for all the joint value assignments to this set R, that the best explanation of H given the evidence E is in fact H star? So does this set of variables, is it independent relative to the explanation? Is the value assignment to this variable, will it not change the best explanation? So this is the problem that we are interested in, and of course the complement problem to see whether the set is map dependent would say that there would be one explanation that differed in the best explanation. Now we examined the properties of this problem, and you can show by reduction from a majority set problem that this is a co-NP complete problem with co-NP with an oracle for PP, complete for that complexity class. It's always difficult to pronounce these classes high up in the counting hierarchy, by a reduction of what we call a suitable decision problem. And there is some interest here for the complexity nerds among us, which I count myself in, because it's not so trivial to find a suitable decision problem. If you look at the map problem, then finding the best explanation, the decision problem that goes with it is to offer the network and the evidence and a number Q, a rational number Q, and ask whether there is an explanation with a probability bigger than Q. But if you want to follow the same approach here, then you would need, for every joint value assignment to this set R, you would need a different, potentially different rational number Q. If you bring that into the input, then your input would expand to exponential size. So there was some interesting quirks here with the complexity proof. But that being granted, it's relatively straightforward to see that this problem is co-NP complete with a PP oracle. It's of a similar complexity class as deciding whether some relationship between evidence and hypotheses is monotone in mode, for example. And the approach is also similar. It's a similar type of problem. You need to have a statement for all value assignments to R, and you need to do probabilistic inference for each of them. So hence these two contributions, two sources of complexity, the universal quantifier, so to speak, and the inference problem. Now, trying to solve this problem, there's a relatively straightforward algorithm that would solve it. So if you have this instance as an input, the output would be yes if the explanations would be map independent from the set R, if that is the case, or no if that is not the case. And the approach, the trivial approach would be just try out every joint value assignment to the set R, compute the best explanation, but now also with the instantiation of the value of R. And then if that is different from the H star that was given as input, then we return no as an answer. If that succeeds for all, these sets are, then we return yes. And it's easy to see that the source of complexity here is the determination of the map problem in this case, and the iteration over all the potentially exponential joint value assignments to R. So if you would look at the fixed parameter tractability, if you look at the the constraints you need to impose on instances to make this tractable, knowing the results for the map problem itself, that says that map is tractable if, for example, the tree width is bounded, if the cardinality of the variables is bounded, and either the number of hypotheses and the number of intermediate variables is small, or the probability of the best explanation is high. If we take into account this additional parameter, the size of the number of variables for which you want to establish map independence, if we see that as bounded, then we can call this a tractable problem, so given these constraints. So to conclude this presentation, so what we saw is that map independence can be seen as a sort of a relaxation of conditional independence if this explanation is conditionally independent from some observation. It's also map independent, but map independence is entails a bigger category. We believe that it may be useful to further explicate variables that are deemed to be relevant for explaining a particular map explanation, for justifying why this is the map explanation and not something else. Problem is intractable in general, as almost every problem in Bayesian networks is, but if we constrain the set of variables for which you want to consider map independence, and if the map query itself is tractable given these fixed parameter tractable constraints, then it can be feasible to use in a typical clinical decision support system. We thought about a number of related questions. So and they are related to Celia's work, as you can see. So for example, if the number of relevant variables turns out to be very high, it might be very difficult to justify a particular decision, because if everything is relevant, then it's difficult to wrap your head around that. So a question could be, if I have selected observations in this network, if I run another test, for example, will this significantly lower the number of relevant variables and make it easier for the system to explain and justify a particular explanation? That would be like a future related question. Or which of the observations turn out to be relevant for the explanation? And I think it's very much related to Celia's work here. Of course, we want to augment this theoretical work and also test it out in practical usage of a clinical decision support system. And that is a work in progress we're currently preparing with the medical hospital in May. Thanks for your attendance, and I'm happy to take any questions.
Thank you, Johan, for an interesting talk, and we have time for one or two questions. Is there any in the audience? Please, Sia.
Hi, Johan. Could you clarify if you meant co-NP-PP or co-NP-PP?
Okay, so what I meant here is the class co-NP with a PP oracle. Yeah, so it is the complement of NP with a PP oracle.
Okay, thanks. I may have followed in your example of the glass. I understood well the theoretical problem, but wearing glasses and attending the festival there. So are you assuming that there is a dependence, but it's just about really the example here? Because I had the feeling that the arc would cut or not, so...
Yes, so what I wanted to do here with this example so in the first example, I showed a variable b where the actual value of that variable, were it be observed, would change the best explanation. In this case, the variable b, if it were observed, would not change the best explanation, or arguably would not change it. And the idea is that we lose sort of that information if we just marginalize out the variable b. But if you would zoom in and try to discover whether it would actually be relevant towards the explanation, and I define relevant to be, would it change the best explanation for some of its observations, then you could argue that if that is the case, then this is a variable that could contribute to justifying, for example, in this situation, why can I not attend a festival, or can I attend a festival? Well, D doesn't play a role in that, but B does in justifying why the decision is as it is. And that's the purpose of these examples, to highlight when it would not be relevant here.
Sorry, but wouldn't it be better than just to, in the case of this B is varying classes, just to remove the arrow from B to A?
So, well, it depends a bit on the actual query you would like to do in a network. So it might be that for some observations, B would be relevant, but for some it would not be. So even assuming that you have like a fixed hypothesis set that you're interested in for drawing diagnosis, it could be different for a different observation C. B could certainly become relevant or not. So it's conditional on the observation. So you cannot just prune B from the network immediately. Well, in this case, of course, it's a very trivial example. You could argue, well, this one here, B has arguably no relevant role in this model, so why not prune it? In a more sophisticated case, you could argue that actually the relevance of B is conditional on what you actually have observed in the other observations.
Okay, thank you, Johan. I'm sorry, but we don't have time for any more questions, so thank you again. And the last speaker of today's last session is Alessandro Antonucci from I rather written it down because the name is quite long, University of Applied Science and Arts of Utrecht, Switzerland. Sometimes it's Switzerland, sorry, it didn't make sense. And the talk is called Cautious Classification with Data Missing Not at Random Using Generative Random Forest. Wow, that was hard. Okay, so I'm glad everyone stayed for the last session. And Alessandro, please go ahead.
Thank you, Martin. Can you hear me? Can you see my screen? May I start?
Yes.
Good, good. Thank you. Thank you, everybody. Too bad I cannot be in Prague. It was complicated just because of my teaching stuff starting. Only because of that, I'm sorry, I cannot be there. Okay, this is joint work, and this is mostly a work by Julissa Villanueva and Dennis Mawad. Julissa is a PhD student in USP, the University of São Paulo. She works under the supervision of Dennis. Dennis Mawad is professor there. I work with Dennis. Dennis actually was a PhD student in my institute at ITSIA in Lugano. Then he went back to Brazil. We share interest on the probabilistic graphical model. We share interest about generalized probabilistic approaches. Both, I think in the last years, we are moving towards from classical probabilistic graphical models to so-called probabilistic circuits. Some people use the term tractable probabilistic graphical models, and generative random forest are an example of this class of models. If I recognize the voice, I think Cassio De Campos is in the audience, and maybe I'm not sure of that, but the invited talk of Cassio will touch this topic, this class, relatively new class of models they proposed very short time ago. We are focusing on cautious, on classification task, on cautious, or if you want vice versa to call it robust classification in machine learning using this class of models when coping with data that are missing and data for which you cannot formulate the standard missing at random assumption. So let me start by talking about missing data. And I will say, generally speaking, most of classical machine learning approaches, they assume the data to be complete. And if they are not complete, they assume they can be somehow imputed, or they just marginalize out the data. But I'm using this silly, actually not so silly example of Trump against Clinton in 2016. Actually, I'm not sure that was because of the supporter of Trump were not really properly answering to the poll that people got surprised at some point when Donald Trump was elected. But okay, this is just a stupid example to say that the classical assumption justifying the marginalization of missing data, which is the missing at random assumption, which basically means that the probability of observing a missing value is independent of the actual value of the variable you want to observe. This assumption, of course, is not always realistic. If your sensor is completely broken, the probability of missing is 1, and this is missing at random because it's independent of the actual value of the X you observe. But let's say if your sensor of temperature got in troubles when the temperature is very high, and you don't know that, actually you're going to marginalize over the marginal for the temperature. And so your result can be very biased and very unreliable because of that. So there are missing, not at random data. Okay, just some notation. I assume that my joint model is over 3 different sets of variables. Let's say Y is the query variable, O are the observation, and U are the variables we don't observe, that are, say, somehow we don't observe. I'm not using a P for this because we are coping with circuits, and generally speaking, the circuits define a joint density which should eventually be normalized. So let's say we have M, but actually if we sum out this unobserved variable U's, we can get the conditional probability for Y given O, and the maximum probability will be the output of our classifier or whatever. This is, if you want, the MAR way. But if you don't know that MAR is a reliable assumption for your missing data, you can consider a more cautious approach. The delta function I'm defining, which is, okay, just the name we give, is a kind of robustness descriptor of how the first class is dominating the second one. Actually, we are considering the difference between the probabilities for all the possible explanation, for all the possible values of the U variables, and we take the minimum. So it's a kind of measure or how strong is this dominance. Okay, if we have this measure, we can be very conservative and decide that the output of our classifier will be made only by the unrejected option, which we intend like the option for which this dominance given the other class is negative. So they are the classes Y such that there is no Y prime which is dominating, being conservative with respect to the values of the unobserved variables. This is a very conservative, the most conservative approach to the treatment of missing data. And we want to check this kind of dominance. And to achieve that, basically, we need a good scheme to compute this delta function. Of course, we can do brute force with respect to the values of U to consider all the possible completion and then take the minimum. But we are looking for a fast scheme or for an hardness proof. We want to prove that the result, this task in a particular class of model is NP-hard. For instance, people, actually I did also long time ago for my PhD, I studied the SEER inference in Bayesian networks. Of course, in Bayesian networks, inference is already NP-hard. So it's clear that this kind of inference is NP-hard. Actually, what you can prove is that once this kind of conservative approach is equivalent to transform the original Bayesian network in a Bayesian network quantified by sets of probability, which is called the Cradle network. And Cradle inference actually inference in Cradle networks belongs to higher complexity classes. So somehow in the case of Bayesian network, the task is hard, of course, also without missing this, it remains hard, but somehow is in a higher class of complexity. I never focused on this. I was thinking actually today, but I think, for instance, for simplified topology, you can prove that, of course, inference in Bayesian networks is simple. I think at least for non-binary variable, probably you can prove that this zero inference became hard. But okay, this is just pure conjecture. I'm not focusing on Bayesian network. I'm focusing on probabilistic circuits. And probabilistic circuits are actually deep probabilistic models based on logical or arithmetic circuits. So basically, you see, we have sum nodes, which if you want are disjunction, and product node, which if you want are conjunction. And the sum nodes are annotated with the value of a probability mass function. And in this way, we can, on the leaves of the circuit, we have univariate distribution. So for instance, when we have this node number 5, you see we have a probability 0.6 for a equal to 0 and 0.4 for a equal to 1. And in this way, you can build a multivariate model. You can define a joint probability mass function. This is, for instance, the idea behind the sum product networks. These are graphical models, but somehow these are also computational structures. Historically, they've been also considering to solve inference in classical graphical models like Bayesian networks. And so it's not surprising that inference in this model is most of the time tractable and basically is linear in the size of the circuit. Inference is like a bottom-up traversal for most of the task. Of course, I have no time to discuss the details, but you need some structural assumption for this model. For instance, smoothness. Smoothness is just to say that some node should have the different inputs with the same scope. So for instance, again, this node number 5 with the plus, the scope of both the inputs is A, is the variable A. While decomposability is for product nodes, and basically the scope of the inputs of a product node should be disjoint. So the node number 2, the blue one, you see that we have one input which is related to A and the other one which is related to B. So they are disjoint. And these are standard assumptions, are the assumption to define some product networks. An additional assumption is determinism. And determinism is basically that when you have a sum node, at most one of the input should be non-zero when you propagate. Okay, these are circuits in general. Let me talk about very quickly, I think you will learn more in 2 days, about generative random forest. And let me start from generative random trees. So single models, these are ensembles. And you might be familiar with classical decision trees. The idea here is very smart, but it's very simple. It is just to convert, to describe a decision tree as a circuit. So for instance, you see now we have this, the first bifurcation on the decision tree between x smaller or equal than 3 or greater than 3 with two probabilities, 0.4 and 0.6. This is a sum node. Of course, in the two product nodes associated to these two branches, we have to put the indicator function forcing x to be smaller than or equal to 3 and x equal to 3. And then we go ahead recursively. And in this way, we create a circuit. But there is an important difference. The decision tree is a discriminative model. The generative random tree is a generative model. So it's a joint distribution over the variable. And in this way, we can do reasoning. We can cope with missing data. And these circuits are deterministic and are by construction with a singly connected topology. These are tractable. Probabilistic circuits are tractable, but in which sense are tractable? Is more complicated. The standard inference, okay, is polynomial time, actually is linear time updating marginal queries, but it depends on the inference task. You need more properties to guarantee the tractability of more complicated inferential tasks. And for me, the question, still at this level unanswered, is what is the complexity of SIR in this model, SIR inference? Okay, generally speaking, and generally speaking means under standard properties like smoothness, decomposability, and determinism, the problem is still NP-hard. Actually, we have hardness. The proof is in the paper. So the general problem for smooth, decomposable, and deterministic circuits is NP-hard. Is it surprising? For sure, it's more surprising that what we get for Bayesian networks. In Bayesian networks, standard inference is hard. Here, standard inference is tractable, but this generalized task is hard. But there is an algorithm which actually is very simple. This structure are recursive structure. So we define this function on the leaves of the circuit, and then recursively we can build the function on moving bottom up. So by means of this simple procedure, we can create a polynomial, actually linear time algorithm to compute this function and hence to solve SIR in circuits, but these circuits, they should be deterministic and they should be singly connected. And the determinism assumption is crucial for making this algorithm working. Actually, in our first formulation, we were assuming that the theorem was wrong and the algorithm was general. But eventually we realized that we need a singly connected circuit, we need the determinism, and so we cannot apply to the general class of model, which is bad news for us. But the good news is that this algorithm can be applied for generative trees and hence for generative forest, which are singly connected by construction. So this is actually, if you want, our main result. Let me see about the time. I think should wrap up. Okay, we have experiment of classical machine learning density estimation benchmarks, and of course, when we do SIR, our classifier is giving a multiple output, and we do comparison against the output we get by simple marginalization. Of course, we have multiple outputs, so the comparison can be done only in terms of this generalized descriptor, which are the set accuracy. We are happy if one of the classes is the right one, or discounted accuracy. We get one divided by the number of classes if the class is the right one. And of course, in terms of discounted, we are less accurate in this case. But what we expect by these approaches is a good separation of the accuracy of the standard classifier when we are robust and when we are not. And by robust, I mean when we give in output a single class, the accuracy of the traditional classifier is higher than the accuracy of the same classifier on the instance of which we don't have robustness. This is the pattern we expect, and this is what we observe. I think I have to be quick. This is just, can be my last slide, and I just want to say that if we ask for very robust instances, so we ask this measure not only to be positive for dominance, but to be greater than some epsilon. Of course, you see the red line is the percentage of robust instances. So we have less robustness, but on the instances which are robust, we have very high accuracy. So it's like we select the accuracy on which we are very, very certain of the result. And this is something you cannot do by traditional approaches. This is a bit more tricky. This is related to another generalized discounted accuracy you have with this model. I think I'm done. So this is actually a new complexity result and a new algorithm for a class of probabilistic circuits. I think we can and we should consider also more others. This is the more conservative, but other mechanisms different from the standard MAR in the modeling, the missingness of the data. And I think these ideas are very related to so-called cradle inference. So we can also apply something to cradle circuit, circuits with generalized probability, like sets of probability. That's it, guys. Thank you for your attention and your time.
Sandra, thank you for the talk. I think you gave us all something to think about overnight, but maybe there are some questions we can answer right now. So is there any question in the audience? I saw Milan taking notes, so I'm quite sure he has one.
Because I mentioned you have this concept of generative random forest. And that seems similar to some work of Schaefer around 2000 something, where he developed condition independence for that. And also then Jim Smith has a kind of decomposition, and this topic of his, it's chain event graphs. So is there any relation to this, or have you been inspired, or it's completely independent, your work, this generative random forest?
Milan, I don't know. I don't know whether, but these models are from Cassio and Cassio's group. This is Cassio is there, no? I don't know.
Here.
I'm not aware of this relation. I don't know. Honestly, I don't know this work you mentioned. No idea whether Cassio.
Yeah, also this is the topic for Cassio and Milan. For the
let's ask him today. I don't know. Sorry,
for the evening. Is there any question online in the virtual space? We should give them give virtual space more space actually. That's weird. But apparently they don't want that space. Okay, any more questions here in the auditorium? Cassio, please.
I can ask a quick one. If you have done experiments to see if your heuristic version that works in the general case, if it's too far from the correct results when you can compute the correct ones.
I think Julissa did something very preliminary. No, actually, let me say the true story. Initially, we did this and we expected that this was exact. And we got decent result. In fact, we prepared a paper in this shape. Then we realized it was wrong, so we stopped with it. But okay, it's something to be studied. As I remember, was enough to justify a paper. Let me say like that. But then we realized that was wrong, and we decided to not discuss this in this paper. Honestly, I don't remember quantitatively, but okay, let's say this kind of behavior was something we were observing as well. Does it answer well there?
Yeah. Well, Cassio knows, so I guess it's okay. So thank Alessandro again. Thank you. Sorry?
No, I just was saying hello, bye-bye to everybody.
Yeah,
There is some question.
Was there?
No.
I think it's okay.
It's close, I think.
All right, so I would like to thank again to all today's speakers, also for the audience that you all stayed with us here and online. We got 35 people in total for this late afternoon session, which is very nice. I would like to thank speakers that they kept their time, so we are able to finish just on time. And now we are for whoever is at the place here in the Czech Republic, we can continue with the banquet. Welcome party. Okay, party sounds better. So I'm very sorry for those who are not here. Yeah, we will have a drink for you. Okay, and
I have very brief good news. Today we just reached 100 participants.
Okay, perfect. We reached 100 participants.
During the
we will celebrate that. It's 100 beers for everyone, no? Yeah. No, that's not the case. Okay, and we are looking forward to seeing you all tomorrow at 9.
yes.
So we will continue, and I'm sure the second day of the conference will be as fruitful as this one was. Okay, thank you all.